Alright, so in this video we go over finding derivatives of trigonometric functions. So the derivative of trigonometric functions all are here in this green definition box. Notice in this case we're using u whenever a function is composite, like having sine of x squared, sine of e to the 5x, for example. And well, these are formulas that we will be using as we progress, as we go along the way. But it would be great if we use the limit definition at least to derive one of them. And in this case, I'm going to derive the derivative for the function sine x. All right, so we're going to use, let's recall the definition of the derivative in terms of x and h. So f prime of x will be the limit of f of x plus h minus the original function x f of x over h as h approaches 0. And in this case, applying this for the sine function, this will be the limit as h approaches 0 of the function. Well, in this case, for the first case, f of x plus h, that means we will replace this x on the sine function with x plus h, that is sine x plus h minus the original function, which is sine x. All right, whole thing divided by h. Well, from here we cannot factor anything or multiplying by a conjugate in this case, because that's really not going to lead us anywhere. So like we did in the limit exercises in previous sections. So what we're going to do is we will simplify this sine of x plus h using a trigonometric identity that you should know from trigonometry. Let me write it down, of course. That that ID, trigonometric ID, that says sine alpha plus beta equals sine alpha cosine beta plus cosine beta sine alpha. And in this case, well, our alpha is the x and our beta is the h. So let's go ahead and write that in these terms. Well, so this will be equal to the limit as h approaches 0 of sine x cosine h plus cosine x sine h. And that minus the original sine function. Well, in this case, well, let's simplify this expression right here. Let me make some space perhaps over here. Let me make this a little bit smaller. So well, so this is what my strategy will be about. Well, I'm going to put this negative sign and sine x cos h, and I'm going to put them together, and then I'm going to factor the sine x, you'll see. So let me just rewrite limit sine of x cosine of h minus sine x. And then, well, I think I'm running out of space here. Let me put this down over here instead. And that minus cosine x sine h. The whole thing divided by h. H approaches 0. And well, so the idea is to make this sine x right here in the first term, in the first couple of terms, a greatest common factor. That's going to look like limit h approaches 0 sine x times cosine of h minus 1 and minus cosine x sine h. The whole thing divided, of course, by h. Well, in this case, what we're going to do is, because we have a difference of two terms in the numerator, I'm going to split it into two limits. So that is okay. I don't know what happened here. So that means I'm going to split this into limit h approaches 0 sine x times cosine of h minus 1 over h minus, or rather, actually this was supposed to be a plus. Let me fix that right here. This is supposed to be a plus. This is also supposed to be a plus. And plus limit h approaches 0 of cosine x sine x, or sine h over h. Well, I'm gonna do a little trick here. Well, not necessarily a trick, but and you'll see why I'm gonna do this, because in this case we are gonna use, remember those special limits from that we did in the previous chapter that we're actually reviewing in this section as well. Well, so we're going to use this to simplify this limit expression. Well, so I'm going to notice in this case we have, let's see, notice this is a product. There's an implied product here. There's another implied product here. And from the properties of limits, recall that the limit of a product is the same as the product of the limits. On the one hand, for example, I'm going to write this limit h. Well, actually, let me go over here. I don't think I'm going to have enough space. So limit sine of x as h approaches 0 times. Notice in this case, what I'm going to do is factor the negative from here. I'm going to write a negative in the front and write this as the limit of 1 minus cosine of h over h as h approaches 0. And then over here I'm going to split the multiplication as well, plus limit h approaches 0 of cosine x sine of times rather the limit h approaches 0 of sine h over h. Alright, so let's recall what these special limits were. So from previous sections, okay, this special limit right here, the one I'm highlighting in this kind of pink color, well, that limit it's a 0. And on the one hand, this limit right here is a special limit. Well, that limit equals to 1. So we're going to be left with the following. We're going to be left with, well, the limit of sine x as h. In this case, the variable is h approaches 0. Well, sine x is constant, so that's just sine x times the 0 right here from the second limit, plus limit of cosine x as h approaches 0. That's also a constant, just cosine, times 1 from the limit in green. Well, this term is going to go to 0 and we will end up only with cosine of x, which indeed this is supporting the fact that the derivative of sine equals cosine. Of course, notice that du dx, that's because, well, whenever we have a more composite function, but in this case we were deriving or proving the limit for just a regular sine x function, just to keep it simple. So let's go ahead and do some derivatives. Let's apply, in this case, all the rules that we have done before: product rule, quotient rule, chain rule, etc. So in this case, well, let's find the derivative of sine 5x minus x squared cosine 3x. Well, all we have to do is see y prime equals the derivative of sine, which is cosine 5x, times the derivative of the inside of the function, which is 5. That's a mini chain rule. And then minus, okay, be careful here because we have a product of two functions. That means we're going to use the product rule. open parentheses, and then we distribute the negative sign at the end. So we're going to differentiate the x squared times cosine 3x plus the derivative of cosine 3x times simply x squared. That's essentially the product rule. And well, to remind what the product rule looks like, so whenever we have a uv prime, this is u prime v plus v prime u. That is the derivative of the first times the second plus the derivative of the second times the first. And well, so that's going to be 2x times cosine 3x, and then plus the derivative of cosine, which happens to be negative sine of 3x, times the derivative of 3x, which is 3, that's a mini chain rule, times simply x squared. Alright, so let's simply clean up the negatives and clean up these parentheses. Well, I'm going to write this 5 in the front, 5 cosine 5x, and then minus 2x cosine 3x, and then be careful here because plus minus, that means a minus with a minus in the front, that's a plus, x squared, and then this 3 can be written in the front, sine 3x. Alright, and that's final answer. Let's look at another example, one in which we're going to use the quotient rule. Okay, let's write down what the quotient rule is. Whenever we have u over v prime, that's a u prime v, very similar to the product rule, u prime v, v prime u, except that we have a minus in between and a v squared in the denominator. Alright, so when we take the derivative for this, let's see. The derivative of e to the 3x over cosine 7x, that's going to be f prime of x, equals, okay, the derivative of e to the 3x, which is itself, e to the 3x, times 3, times cosine of 7x, because this is u prime times v, and then minus v prime, the derivative of cosine, which is negative sine, so of 7x, times the derivative mini chain rule of 7x, which is 7, and that times just the u function, which is e to the 3x. The whole thing gets divided by v squared, which is cosine of 7x quantity squared. Okay, so there's really not much to simplify over here other than just clean up some parentheses, some negative signs, and yeah, that's it. Even trigonometric identities, I don't think they're useful here. So let's just, okay, I'm gonna factor out an e to the 3x, and that's gonna be 3 cosine 7x minus minus, be careful, that's going to become a positive, and this 7 can be written in front of the sign as a 7 sine 7x, and then the whole thing divided, well, we can just write cosine squared 7x, and there's again not much to simplify over here. Alright, let's have a look at one more, another quotient rule, 1 plus sine x plus, or divided by 1 minus sine x. Well, so in this case, again, we're going to use the quotient rule, so f prime of x equals, well, so using that quotient rule, let me move it again, let me move it down here so we can have that in handy. Let me move it there so we can just use it as a reference. Well, so that's the derivative of the numerator, which is, okay, the derivative of 1 is 0, the derivative of sine is cosine, times the denominator, which is 1 minus sine x, minus the derivative of the denominator, the derivative of 1 is 0, the derivative of negative sine would be negative cosine, times the numerator, which is 1 plus sine x. And then let's divide the whole thing by 1 minus sine x quantity squared. Alright, and then in this case we can leave that 1 minus sine squared over here. I know what you might be thinking, maybe square the binomial, but trust me, this is really not going to do anything interesting. So let's see. So what we're going to do next then will be to distribute cosine times 1 and cosine times sine, negative sign, and then multiply this to negative to have a plus, and multiply this cosine times 1 and this cosine times sine. Alright, so let's see what we get from here. So so this will be, let me double check my work. Okay, yeah, that's fine. Okay, that's fine. So f prime of x equals to cosine x minus sine x cosine x, and then plus cosine x, and then because that's cosine times 1, that's simply cosine, negative times a negative becomes positive, and finally cosine times sine, and that's a plus sine x cosine x. And then the whole thing divided by 1 minus sine of x quantity squared, and that's fine, like I mentioned before. Notice here what's going to happen. That's going to be a very interesting here. Oh, that's supposed to be a plus cosine. Yep. And that's yeah, that's also plus, everything plus except the second one. Well, notice how these two cancel, because sine x cosine x minus sine x cosine x, they cancel. So that's gonna be left with cosine x plus cosine x. That's 2 cosine x divided by 1 minus sine x quantity squared, and call it a day for this exercise. Alright, so let's see what's next. Oh, the next one, letter D. What do we have? We have a really crazy looking chain rule problem. So I think for this kind of exercise, you will see the power and the extent of how can we use the chain rule. Alright, so let's find the derivative for this. dy dx. I'm going to use a different notation. I could have used y prime, that's fine. Alright, so notice what do we have. We have an exponential as the outermost function, and then the inner function is sine, and then an innermost which is cosine, and then an innermost which is another exponential, and finally the innermost which is the x squared. Alright, so let's find the derivative of an exponential. So number one, a times itself. The derivative of the exponential is always itself, e to the 4 sine 6 cosine 7e to the x squared times the derivative of what we have on the exponent, and well, that's 4 times the derivative of sine, which is cosine of whatever it's still inside, and then the derivative of 6 cosine, which is negative 6 sine, and then we need to differentiate the exponential, that it's still the same, 7 e to the x squared times the derivative of x squared, which is 2x. And there's really not much to simplify over here, other than just multiplying the coefficients 2 times 7 times 6 times 4 times 8. Of course, there's a negative going on in there. dy dx is negative 2688 e to the 4 sine 6 cosine of 7 e to the x squared, and that times cosine of 6 cosine of 7 e to the x squared times sine of 7 e to the x squared, and times this factor of x that was left over. There's really not much to do over here because there's no way we can use even identities or anything like that. Alright, so let's look at another example. So the next example is another derivation of a differentiation rule. And now for f to derive or to find the derivative of tangent, in this case, we're not going to use the limit definition. Of course, you're more than encouraged to use the limit definition. Let me just set it up for you. How would it work? How would it look like if we were to do this using the limit definition? But we're not going to take this approach. Of course, I mean, there's formulas for tangent of alpha plus beta, you know, in a very similar way that there are for sines and cosines of the sums and difference formulas. But again, if you want to do it that way just for fun, I highly encourage you to do that. But I'm going to use other rules in this case. So I'm going to use the quotient rule and trigonometric identities instead. So let's see. So f of x equals to tangent x, which can be written as sine x over cosine x. So we're using a trigonometric identity, and then from here, because we have the quotient of the function, so that's why we are going to use the quotient rule. Well, so let's see. So again, let's recall the quotient rule. So f prime of x equals the derivative of the numerator, which is cosine x, times the denominator itself, which is cosine, minus the derivative of the denominator, which the derivative of cosine is negative sine, times the numerator, which is simply sine. And you'll see what's going to happen. Oh, don't forget the denominator squared. Cosine of x, quantity squared. All right, let's leave it like that for now. So cosine times cosine equals cosine squared. Negative times negative is positive. Sine times sine, which equals sine squared. And then the denominator is, okay, I'm just going to write cosine squared of x. And then, well, in this case, notice this quantity in the numerator, cosine squared plus sine squared. It's a very well-known identity that you have covered back in pre-calculus. Well, that equals to 1. All right, so that's 1 over cosine squared x, which we can still use identities. Notice cosine, 1 over cosine is equivalent to saying secant, but in this case squared. And that's final answer. That's the derivative of tangent. Let's verify that. So if we go back to the differentiation formulas, the derivative of tangent is secant squared. But of course, I'm using the easy case when u is simply x. But because of course u can be another more composite function. That's the purpose of having u's in this case. All right, let's do the last example in our lecture for trigonometric derivatives of trigonometric functions. And this is a very classical question in which they're asking for the values of x for which there's a little typo here, should be another h. This given function has horizontal tangent lines. Well, horizontal tangent lines, so of course whenever we have this, this function, there is horizontal line, for example, over here, over there, and yes, over there, and there's another one here, and there's another one there. That means horizontal line when the slope equals 0. In other words, when the derivative dy dx is also equal to 0. So in this case, so I mean, that's the visual, that's not the graph for the given function, that's just the generic idea, So let's take the derivative g of x, g prime. That is the derivative of x, which is 1, minus the derivative of sine, which is cosine x. And well, in this case, we need to set the derivative 1 minus cosine of x. equals to 0, and in this case solve for this trigonometric equation. Well, so let's subtract 1 from both sides. That's going to give us negative cosine of x equal to -1, and well, that means cosine of x equals to 1. All right, so we need to determine where is cosine equals to 1. Well, from the unit circle, cosine equals to 1, cosine is equals to 1 for 0, 2 pi, 4 pi, 6 pi, actually all multiples of 2 pi, you know. So in this case, so that's for x equals 0, 2 pi, and where else? So 4 pi, etc. We can express this more in general for x being in 2k pi, where this x equals 2k pi, where k is an integer. All right, any integer multiple of 2 pi will be where this sine function, x minus sine x function, has tangent, horizontal tangent, that is tangents whose slopes are 0. And of course, I mean, we can have this with more elaborate numbers. All we have to do is go back to solving trigonometric equations and whatnot. All right, so this is a good place to quit the video. I will see you in the next one.